Good afternoon. I gave up on waiting for the next 1,500 people to come. Apparently they're late. They missed the room in the wrong place. Yes, this is Fastware, the best course at this hour right now. Friends, thank you for being here. I'm very excited about this presentation. It's actually rather new material, and there's a lot of it. So I was kind of very anxious to start as early as possible so we can talk. I'm going to talk a bit about the art of benchmarking. I noticed there's a lot of mistakes people do when benchmarking code. And I just wanted to make a few quick points. This is not really like the meat of this talk here, but I think it's important as an introduction. So I'm sure many of us have heard of Amdahl's law. It's used usually in parallel computing. Who can shout Amdahl's law? There's a guy literally in the last row. I assume he would say something like, if you have two components in a system and one is 80% contributing to the time spent in running the system and the other is 20%, even though you improve the second subsystem by 100%, that's, your gains are limited theoretically to 20%. I would say it's the Amdahl's. I would call this a different way. I would call it Captain Obvious's law. Right? It's an obvious law, but it's amazing how often people lose track of it and simply forget the simple reality that if you have a number of processes that contribute to a computation, definitely the critical path is going to be where you want to spend your time on optimizing. I've seen a lot of people dedicating inordinate amounts of time speeding up, and I'm not kidding, command line processing. This is not a joke. There's been a discussion, actually, you can find it. There's records of it online about people who are like, oh, this command line processing, I can make it faster. And it would take, instead of 2 microseconds, it would be 1 microsecond, which is, by the way, it's 100% improvement. Right? It's an amazing percentage-wise improvement, but of course it doesn't matter in the grand scale of things. So I don't think I need to insist on the law of Amdahl. So whenever you want to optimize pretty much anything, even in life if you wish, you must measure. Right? So you can't, the classic dictum goes, you can't improve what you can't measure. And that's definitely the case with performance. I've seen a lot of people spending time on improving things without having a clear idea or where they started from or what was the purpose of going to a faster code, etc. So I'm sure I don't need to, because those are bad people. They're not in this room. Present company is awesome, right? We're doing great. Thank you. So choose hotspots from the whole application. There is, however, a complementary law, Ladma's law. And Ladma is not an Indian researcher. It's just Amdahl spelled the other way around. Just a reverse, right? STD reverse, right? So this is a less obvious law. And it goes, well, you got to optimize hotspots outside the application and then plug it back and measure again, which is not intuitive. Who can give us a perception of why that would be? Why would I advise people to do that? Ideas, thoughts? So I want to make it clear. Let's say I determine that a particular algorithm is critical to the runtime of my application, and I need to spend time improving it. So I say, don't improve it inside the application. Take it out into a smaller benchmark, improve it, and then plug it back. Measure again, make sure the improvement's carried, which is there's a story to that. We're going to get to that, and then be happy, right? So why would I advise people to do that? Well, yes, please. My benchmark stimulus would need to, so that's a challenge more than my benchmark input would need to simulate what the application would do, correct. But that would be a requirement for this whole process of, yes, Patricia. You want to remove noise. Exactly. So a central thing that happens in modern computing is that there's a lot of noise going on about. And it's very often that you have this 20% speed up. It doesn't come as like you have an idea and it improves the thing by 1/5. It comes at 9% improvements. Why 9 and not 10? The math is not right. Is it? Compounding, thank you very much. So they compound, so it's actually 2 to the power of 1 point something a little, and you get to 20% by only 9 iterations in a 2% improvement cycle. So very often you want to take the algorithm from the noisy environment in which it resides and be able to crank 1% and be able to measure that and be able to be confident that that particular 1% improvement is going to count and be carried into the final application. So also there's a number of practicalities associated with this. The edit and benchmark cycle is slow in the whole application. So definitely you want to have a quick iteration in measuring performance, so you don't need to. So you can, you can try many ideas fast. It's amazing how much friction that how much friction can impede your way of thinking. All of us know, like, slow compile times. Come on, right? The slower compiler is, the more your mental flow gets more disturbed, right? But so this would be the counter effect here. Do not forget that optimizations have global effects. There's cache effects, there's memory allocations, and the allocations, there will be branch predictor hogging, there will be lock contention, etc., etc., etc. So that's why after you improve your thing by 20%, you got to carry it back in the application and see what happened to those 20%, right? True story, I've been working at Facebook on the HHVM compiler, which compiles PHP code into a JIT. And we can't do that. That is not possible to do, because the application is so high, it's dominated by the global effects. And the main thing that the team had to fight against was cache misses on the instruction cache. It turns out large code was the main, #1 by a large margin issue. So think of this. If your main problem is I have too big code, is the first step you want to take, oh, let's take the portion of the big code and make it smaller, measure that. It's nonsensical, right? Doesn't make sense. So therefore, we had to measure on the whole application. There's an entire team, I'm not kidding, an entire team with scientists and statisticians and stuff dedicated to not optimizing. That was a different team. I wasn't that. There's another different team dedicated with being able to measure minute differences in performance. And the way it goes, you send like 500,000 pages with the baseline, the existing code. You send 500,000 pages with the new supposedly improved code, and you're trying to find the deltas. And you're looking at, really, really small. And the best we could get to was 1%. So if it was less than 1%, we would throw it away, because it was not demonstrably better. So, those are the days. So anyway, so I'm just saying that most of the time you don't have that kind of problem, but sometimes you do, right? So a slide that is not here, because it's, I shouldn't mention this, and you're not victim of this, right? Not even your coworkers, your former coworkers are the bad people, right? I've seen time and again, and it bears mentioning, people still measure the speed of debug builds. You have no business measuring the speed of a debug build. It's like I spent once 1 week because a coworker kind of said, oh, actually this thing is really much slower than the baseline. Why did we make that change? I was like, oh, so we got to look into this. And finally, oh, wait a second, I was measuring the debug build. The debug build is not even supposed to be fast. So it's not, there's no purpose in it being fast, right? So you want to measure that. There's a lot of different people who do different setups for baseline and measured. By which I mean the following. For example, Consider this. You have your baseline, which is the sort of the existing algorithm, the existing code. Then you start the timer, and you stop the timer, right? So we have that. And then right after that, you start again the timer, and that's your code. And stop the timer, compare the two. What's the fatal mistake? What is the fatal mistake? Paul?
The heap, for example.
The heap. Thank you. Yes. Yeah, the moment you say the keyword, I mean, I know you, I know what you're up to. So the moment you said the keyword, I knew you have the answer. So essentially, consider this. Consider that the baseline is going to allocate memory. Malloc, new, whatnot, right? Allocates memory, and then it deallocates it. So it looks like everything went back to normal. But no, it didn't go back to normal. The heap right now is in a completely different state because much of what a good memory allocator does is collect, hold on to memory that was allocated and then deallocated and put it in neat data structures that are ready for the next fight, right? So they have like free lists, they have, all of the, not to mention the cache is warm, not to mention a variety of other effects, right? So you don't want your former coworkers to do that kind of stuff. Agreed? Yes, thank you. Not to mention things like worth of cache, files, databases, DNSs, and all that stuff. If you do a lookup in the baseline, then it's going to be much faster the second time. You should know there are techniques on every operating system and file system to essentially cool the file cache. How would you do it on Windows? Restart the machine. That's going to work. And that, absent anything else, I would do that. Yes. There is a technique that I don't use Windows, but I know there's a possibility to dismount and remount drives in Windows. Right? Is there, Paul? Is there? Okay, so here's the thing. My hope was that there's going to be a person in this room who's going to be, yeah, of course you do X, Y, and Z. And I'd be like, you do what that fine person said. And now I'm kind of lost because I do know how to do it in Linux. You mount and unmount the file system.
You can just read lots of other files.
You can what?
Just read lots of other files.
You can read lots of other files, but that'll be slow, right? Yeah, actually that's valid too. Then absent any other. But in principle, Linux uses all of the unused RAM as file buffers, caches. So, and the way to get rid of that is you unmount the drive. So you unmount, you remount, and then it starts cold. That's great. Okay, but still that's not the topic of today, which we're getting, don't worry, we're getting there. Another pitfall that I saw your former coworkers doing is they include ancillary work in measurement. Probably like statistically a bunch of measurements measure like the speed of printf, right? All that kind of stuff. So, of course, this is not something that any of us would ever do. I've seen also a procedural mistake. When I say procedural, not in the sense of procedural programming, procedural by means of like human procedure, like way of doing things. A procedural mistake, and what I think is really distinguishing between scientists and engineers. A scientist would be like, like Sheldon in that show, right? So very obsessively changing one parameter at a time and measuring again. I've seen people, I changed like 10, I had 10 ideas. So I implemented them all and let me measure again. And then you have no idea which actually helped and which not. And maybe there's even two that cancel each other, right? So you don't want that to happen. So you change one thing at a time very rigorously and you proceed like that. Not to mention optimize rare cases and pessimize others, the frequent cases. Hat tip, credit to Stack Overflow, which featured the following very interesting discussion. There's a programmer saying, why is sort slower than is sorted on sorted arrays? So the experiment would be, I sort an array, I run is sorted, which checks whether it returns a bool, right? And also I sort the array. And by some reasoning, it would go, well, sort should do absolutely nothing if the array is already sorted. So it should have the exact speed of is sorted. And the solution envisioned by that fine programmer was the first line in sort should be if is sorted return. I'm sure you see the irony, right? Because that's going to work exactly once in a lifetime. For it just so happened I passed like an idiot and already sorted the array to sort. And yes, that was fast, ladies and gentlemen. Thank you very much. But actually, it pessimized everybody else because it makes an extra pass to the array without actually doing anything of interest. All right. That's the example I meant to. The guy actually collected a graph, which is very nice of him. So sort is slower than is sorted. Yes, that's true and is expected. So today we're facing impossible odds in optimizing our code. Today's computers are too complicated for our poor minds. I'm not kidding. This is like really a terrible point in history to be at. You know what I want to be? I want to be in like the 70s. The days of Zilog. Z80. The 80s, sorry. The 80s. Great music too. So I want to be in the 80s, and the good days of the 80s, we had the Zilog Z80, one of the first microprocessors of any success. And back then, there's no pipelining. You knew exactly how many cycles each instruction took. You had zero-weight memory access, friends. Amazing. You could get all the way to memory and back, fetch the data. It all happened in one cycle. No cache, no, all of that nonsense did not exist. No speculative execution, no branch prediction. Oh, what's with all that crap, man? You know, none of that. You could actually quite literally read the program and see, oh, this is going to take 253 cycles to execute. You knew exactly what we were getting, right? So, well, fast forward to nowadays. Wow, they got to a point where, amazingly, we have like you can't measure it's impossible to obtain the same measurement twice when you measure speed, right? So you even have things like dynamic frequency control. Who knows about? So yeah, thank you. So whenever you measure, whenever the CPU runs, it figures it's idling. So then it slows down, which, as an aside, is a very, very human thing to do. Let's take a nap, right? Let's take a little break. So it runs at a slower speed, and then when you kind of start again and detects there's work to be done, like a loop that does things, you go, oh, let me accelerate, and all that stuff. So it's virtually impossible nowadays to get identical timings for the same experiment. And by the way, this was it's a marketing thing. There's a consistent trend since the 80s to trade reproducible performance for average speed. And not everybody did so. So this was a marketing. So essentially it was like that. People use desktop applications, they use Excel. And we want people to essentially perceive that on average the computer is fast. However, there are some applications in which you do want reproducible performance. And Cray, the supercomputer company, they did have such a clientele. And Cray had no cache for many years. I'm not sure if even today they gave up, but they had no cache. They had it was all deterministic, right? So Cray is not a sort of a titan of computing nowadays. So in a way, average performance won. So one great thing that should not help you is intuition. Silicon is not intuitive. It's very difficult for a human being to develop a good intuition of how a CPU is gonna run. So we make almost without mistake, we make narrow, obsolete, wrong assumptions. For example, a common dictum is fewer instruction means faster code. Is that true? Who's with me? Fewer instructions are faster code? Yes? One instruction. What if that instruction is fetching from memory? Sorry? You get to pick the instruction. Ah, that's cheating. OK. You win. Okay, so definitely that's something that's, it's more subtle than that. But that's actually definitely not always fewer instruction means faster code. But there's also a proxy phenomenon. On average, if you get to reduce the number of instructions, there's only this much you can go without actually accelerating the code. So it's a good proxy to look at, but it's not definitely an immutable truth. So that doesn't go. How about data is faster than computation? Caching, memorization, the nice things, right? Of course, I don't need to pause and ask people and stuff, because you know very well that sometimes the data actually is too much, there's too much of it and there's cache effect. So data is not faster than computation. Some computation, but not all, is faster than data, but not all, right? So you got to find the right balance. And there's one good intuition you can have, which is, I should sit down and time this stuff. That's the best, that's the one intuition you can use. It's been very many, and I do this for a living. It's been very many times. I've been like, let me measure this crazy, stupid idea that I'm sure is going to be terrible, and it went well. And vice versa. Most of the time it was vice versa. Let me try this awesome idea which I have, and it just works, and it's amazing, and it's fast, and it was just 4 times slower. It's actually, it just keeps on happening. It's like, I don't know, it's karma. Maybe I've done something really bad in a previous life. So measuring is going to give up on a leg up on experts who are too smart to measure. That's a classic quote. So, that said, there are a number of heuristics you can rely on. And when I say heuristics, I mean things to look at without blindly following them or believing them. They are proxies, they are heuristics, for example, math is your most important ally in optimization. We are past the day when we would do things like self-modifying code that would, write a bit here and a bit there in assembler and machine code. I think we're past that age. I think we're in the age of math. I think virtually like all optimizations of interest nowadays are motivated by mathematics. And by mathematics, I mean the following. You do a transformation on the code that you know is going to make the code faster, and you use math to prove to yourself and others that the transformation preserves the semantics of the code. Right? Also, you can use things like mathematical identities. Yes, because math doesn't care about expenses. Math is like, I'm going to do a superfactorial, no problem, I can prove things about it. And math doesn't care about how much you spend computing things as long as it gets the proof right. So math doesn't say what's interesting and what's not, and what's cheap and what's not. Math does tell you only what's there and what's not, what's true and what's not. So that's how you use it. I think we're also kind of moving a bit away from a variety of mini tricks that people use in optimization. We're moving again toward a more principled approach. I'm talking about the last maybe 5, maybe 10 years. There's been a sort of a trend. Another heuristic that you can use is that computers like boring and they don't like surprises. Computers like boring. The best thing to optimize for a compiler is a main function that's 1,000,000 lines and it has no branching, no if, and no else, and no nothing. Don't write code like that, but this would be like ideal because just straight line code, it just goes and goes and goes, and all the compiler has to do is fetch the next instruction, execute it, and retire it. And the CPU is very good at that kind of stuff. So they hate surprises, which come in form of branching. You don't know where you're going to go, right? Dependencies, I need to do this first and this second. And by the time, I can't do anything here without finishing this, right? So in a way, this guy is surprised by the result of this operation, right? Indirect calls are the worst. We've been talking with a couple of colleagues, like, no matter how good CPUs get, a pointer to a function is going to ruin their day. You have a pointer to a function, you're having a good time there, and as soon as a pointer to a function comes into play, it's like, oh my goodness, this is so slow. Like I'm not sure why they can't figure out a way to make that like 100 times faster, because it is real slow, right? I was kidding. It's a hard problem, right? So the thing is, again, it's a surprise because you don't know what function you're calling, so this kind of stuff. I'm gonna afford myself. We're a bit in a hurry because there's so much material, but I'm gonna afford myself a minute to tell you a story that I think it has meaning. So I had a paper on median finding, and I was talking to a researcher about an improved sort algorithm. And part of that improved sort algorithm would be the insertion sort part, which is the end game of quicksort. Right? Quicksort is not very good for small inputs. Like you have like 50 items or 30 items or 20 items, definitely don't want to use quicksort anymore. You want to switch to an algorithm that is bankrupt big O in a big O way. However, when the numbers are small, is 20 times 19 is not too bad, right? Meaning like 20 squared, right? So the endgame for quicksort would be insertion sort, which goes the following way. It goes, you start from the left. So again, imagine like 20 numbers. So you start from the left, and you're going to build a sorted array by inserting from the unsorted portion into the sorted array. And that's your insertion sort, and it's quadratic. And every time you're going to do the next insertion, you're going to have to search the value to insert into the already sorted array. Make sense? And then you're going to move the rest, right? You insert it and move the rest, right? Understood? This algorithm is pretty well known. Even though you didn't write it in a while, of course, I didn't write it either in years. But I remember it from the drunken days of college. I do remember, I'm fluent with it, right? And we all are. So now, insertion sort. So this researcher implements an insertion sort that does the following. Whenever it needs to insert the next value, it starts from the end of the already sorted array and searches for it linearly. And then finds the insertion point, inserts, moves on, right? But I'm so clever. I said, you, mister, are not getting it. You do need to do binary search. Binary search is going to go in the middle of the already sorted portion, and it's going to do dramatically fewer comparisons because it's binary search, log n instead of linear, right? Guess which algorithm was 4 times slower? Yes, mine. The binary search was not only a bit slower, not only depending on things slower, it was unambiguously, unequivocally way slower than the naive, I'm going to do a linear search from the back of the inserted array. My question to you in the challenge, it took us days to figure out why, so I'm going to give you 30 seconds. Why do you think that? Yes? You don't get any prefetching. No, we're talking small arrays. It was really, there's no cache issues. Branching. What about branching?
The fact that it doesn't know, in the linear, he knows always where it has to go, while in the binary search, it might go one way or the other.
Excellent, thank you. So the answer was, it's the surprise that comes with branching. Consider this. When you do a loop that goes from the end of the sorted portion and does a linear search, how many times do you fail to predict? You may fail at the beginning. The first comparison, you may fail to predict it because you have no idea what state you are in. So in the worst case, you're going to fail once, and then you go and you're going to go. You succeed at predicting that it's going to keep going. You succeed at predicting, because the predictor works whenever you succeed to do something, you assume it's going to go again just as fine. So it assumes it goes well, so the loop is going to go with good prediction until the found portion, which is the second fail of predicting. There's 2 failures to predict. However, when you do binary search, every search is interesting. Every test is interesting and surprising, because depending on it, you go left or you go right. So it's not boring. So you may fail, and you are going to fail you can prove very clearly that you're going to fail multiple times to predict the next comparison, because it goes all over the place, right? So that's kind of an interesting lesson whereby not only I used an algorithm that was theoretically faster. It probably did, I measured the number of comparisons. It was dramatically smaller. However, the realities of hardware settled in and changed the outcome. Was this an interesting parenthesis to spend time on? I think it's an instructive kind of thing. You know. Okay, so computers like boring. They don't like surprises. That was the top point. Indirect writes are slow. Strength hurts. When I say strength, I mean difficult operations, right? Division hurts more than multiplication. Multiplication hurts more than addition, etc. Small is beautiful. Small code, small data is beautiful, though that may change. There's been, I've read a few articles about this already. So there's the advent of some new kind of memory types which are so fast that you need 4 CPUs to drive them. And they're used currently in very specialized applications, but if those become mainstream, we may not have a memory hierarchy issue anymore. So that may change in the future. We're going to have memory that's so fast you actually can saturate it. So that's the sort of the most recent development I know about. Cool. But before that, don't forget, whenever you benchmark, keep the following in mind. The goal is to estimate the speed of some algorithm, and the usual procedure is choose experimental conditions, run experiment multiple times, and then take the average. And by the time I'm done reading the slide, I have made a fatal mistake, which you will tell me about. Livio. Victor, sorry.
You need a baseline for the measurement?
You need a baseline. Assume we have a baseline.
What's the average?
You're not allowed to questions. Right? I'm like Trump here. So, OK, go ahead, Victor.
The average is wrong.
The average is wrong. Why is it wrong?
Because outliers may affect it.
Outliers are going to affect it. It just turns out that noise in computers is weird in several ways. But one is, first of all, it's always additive. So there's no noise in a computer that makes things run faster than they theoretically could. And if you know a way, you're a billionaire, right? You could make money off of that. It's like, there's like this crazy network activity in my computer, and it ended faster. It's amazing. How do I patent this, right? So all noise is additive. So it doesn't look like a Gaussian, like most people like model noise. It must be a Gaussian and all that. No, it's actually half a Gaussian. It's actually a kind of a different distribution, Poisson. But essentially, it's like it's a half a curve. And the second thing is, when noise comes, it's humongous. Like we're talking. Here's the thing. Imagine I stop talking right now. I go get a burrito, eat a burrito, have some coffee as well, and come back, continue my talk. And I say, sorry for the interruption. Right? So it's this long that actually whenever I have, for example, a timer interrupt that's going to, do a system call to advance the clock and the time zone nonsense, all that stuff that's happening on your computer on a regular basis. And if it just so happens it interrupts your test that wants to figure out how fast is an addition of 2 floating point numbers. You see what I'm saying? On average, when Bill Gates hops on a bus in Seattle, everybody on the bus is going to be a super billionaire. Right? On average. So the outliers are so punishing. We're talking many orders of magnitude that even considering them is going to profoundly alter measurements. So I'm not going to insist on this, but please, taking the average is about the worst thing you can do when measuring speed. What do you want to take then? Mean. Other thoughts, ideas? Here's a thought. How about you take wherever you measure the most samples, the most density? So the most, you have experiments, and some numbers appear more often than others. So maybe you take that. It's called a mode of the distribution. The mode is great. What other ideas? Median. Mean, median, right? Minimum. Minimum is actually an interesting idea. Most of my experiments take the minimum, because the minimum means the least noisy result you ever get. And if you optimize for the minimum, definitely you're going to get a better average, right? So anyway, all right. We discussed this, we discussed that, we discussed that. Great. So if not average, we discussed mode, we discussed, actually I did some measurements myself, and it turns out that whenever you take the mode, if you measure many times, the mode tends to go to the minimum. Right, so slowly the mode, the maximum density of samples goes to the minimum, because if you measure very many times, the noise is going to get canceled because it's all over the place, so you're going to get a mode that's very close to the minimum. However, there's a class of algorithm that doesn't work with the minimum at all. Randomized algorithms. Who can give us an example of a randomized algorithm? Example of a randomized algorithm. Yes, please. Monte Carlo simulation, in which you randomly change the, yes, thank you. Great. Something more like humane, more not humane, sorry. More like, you know, because not everybody is going to run Monte Carlo simulations. But there's one like sort. Thank you. Sort, did you primality test. So you randomly, I didn't know that, but yeah, sounds completely. There's algorithms for example, the traveling salesman, because airlines need to do that. And the traveling salesman is NP complete, so you can't really sit down and do it. But there's a randomized algorithm that is guaranteed to give you, in the worst case, twice the optimal solution, twice the cost of the optimal solution. So it's pretty good result. But sort is like a very simple example of randomized algorithm. There's also like a lot of networking protocols use randomization. They use exponential backoff and whatnot. So there's a lot of random elements in networking. And you don't want to take for those the minimum. Because consider sorting. When you sort, you quick sort, and you take the pivot and you take it at random, which is a good technique, actually. Some libraries do that. You sort many times, and do you want to pick up the lottery winner? Right? It's not a good idea to pick up like the most lucky case. He just got the pivot straight down the middle like 5 times in a row. Right? So that's like a very rare case, in fact. So you don't want to pick up that case as your representative runtime of the sort algorithm. Right? So for those, you got to go with things like, I want to throw away the largest 5% times. And actually, if you plot the histogram of times and frequencies, you're going to see that there's going to be a few outliers, and it's going to be very visible where the weird noise is, and just cut that away. It's going to be in the few percent, the top few percent. Average over the last, or thresholds a la P95. So in networking in particular, it's very interesting to take things like 95% of our measurements were below this time. Right, that's P95, and that's very nice for networking when you want to make sure that your site works properly across a number of countries, for example. Great. Okay, with this, the talk starts. We're starting right now. So, by the way, you're in the Fastware talk. This is it. I'm sure. Okay, nobody's leaving. Great. So the first tip I'm going to give, which is concrete, we're going to have code. So far it's just vague. But we're going to have code. So tip number 1, replace branches with arithmetic. And the idea is, instead of a branch, you want to integrate the result of the branch as a 0 or 1 value. So that means, essentially, you do the test, and you initialize an int with the result of the test. Instead of doing if on it, you initialize an int with it, and then you use the int in computation. And that int is going to be 0 or 1, right? So that means there's less pressure on the branch predictor. There's no branching, so there's no need to do branch prediction. There's less fail speculation. There's no, it's just straight line code, and there's fewer stalls. So let's do a statistical task here as an example. Swap the minimums of 4 to the first quartile of an array. So we have an array, and the first 25% of the array should contain, each element should be the minimum 4 elements of the entire array. That's an important step in doing things like approximate median and stuff. So what I have here is, to the joy of some of you programs who are C# programmers, I chose to use C# as an example. C++ people are going to definitely figure out the code, but since this is mainly a C#, how many of you are actually C# programmers? Okay, so my branch predictor was right. How many of you have no idea about C# and hate myself for doing this? Okay, no, nobody. I put an and in there, so that's difficult to answer. Okay, so using C# as a backend language, I'm going to take the minimum of 4, given an array of doubles, I'm going to fetch the length and then use 4 induction variables, which are going to go from 0, n by 4, n by 2, and 3, n by 4. I, j, k, l. And then I'm going to do a loop that's going to simply deposit the minimum in the leftmost position. And how many branches do we have inside the loop? Let's take a look. We have an if here, and we have an if here. So that would be 2 branches. Oh, 3. 1, 2, 3, right? Great. So that it takes 3 tests to figure out the minimum of 4 numbers. And now a word about how you test the speed of such an algorithm. You must test on some, because there's actually, this point was made in the beginning, which was your test data must be representative of the actual input. And what I did was to test on the following 5 inputs. Organ pipe is a data set that goes up and then down. It's an artificial data set that does this, just to make sure I'm not optimizing for already sorted arrays or something. The second is simply random data uniformly distributed. The third test is more interesting. It's random 0-1 data. It's random zeros and ones. So that even though they're floating point numbers, it's just zeros or ones. The idea here behind a random 0-1 is that I want to test data with a lot of duplicates, but at the same time, it's unpredictable. Right? There's plenty of duplicates because half are going to be zeros, half are going to be 1, but I have no idea where they are. So this is a great test for the branch predictor. If my algorithm is branch predictor happy, then random 0-1 is going to mess it up. Right? It's going to destroy it. I'm also going to measure on sorted data, and I'm also finally going to test against real data. And what I measured here was word frequencies in the English language as per Google. There's a data set from Google. So I just collected, essentially billions of pages, and I got the word frequencies in English, and that's a real, that's a real data set that has that obeys some natural statistics, and I tested on that. So you want to test on everything there is, right? And this is a good. Don't forget, if you don't, you'll see. What I'm saying is that if you, for example, if you test only 2 of these, you get no information. You got to test on everything. So, okay, part 1, I'm going to make a few passes kind of mimicking my mind as I was doing this. So first of all, let's do some sense and sensibility. One thing would be I want to, oops, okay, there you go. One would be I'm going to store this p.length by 4 in a variable so I don't compute it multiple times. I'm doing some manual common sub-expression elimination if you wish. So I'm going to go for int I equals 0, j gets n by 4, n by 2, 3, n by 4. And I'm going to say for I less than q, so the q limit is pre-computed. And then I increment everything and I do the rest. It turns out that the speed is the same, but indeed I convinced the compiler to use less space, so it's good. By the way, these results are reproduced on the C++ backend as well. So everything I say about, any comment I make about the speed and speed improvement applies to the C++ backend. So it's not only C#. So same speed, smaller space, awesome. So it's a good step. Just apply sense and sensibility. Don't compute the same thing many times. Don't do redundant work, that kind of stuff. Right? Motherhood and apple pie. Pass 2, reduce dependencies. So I need to take the minimum of 4 items. So how about this? I'm going to first compute P of y versus P of j, and in a different branch, P of k with P of l. So I'm going to compute the index here. And then I'm going to do the final test here. The idea being that the two comparisons are not dependent on each other. They're like four distinct numbers, and compared them 2 by 2, and these comparisons are not dependent upon each other, so they run in parallel. Or so I wished. They didn't. So it turns out I got the same speed. This is one of those things. You got to measure because you don't know exactly what's going to happen. So you get the same speed. Fine. Pass number 3, I'm going to try to reduce the induction variables. So there's too many i's, j's, k's, and l's being incremented there. So let me just use I and look at my for loop. It got dramatically simpler. So I have I equals 4, I less than q, which is a quarter of the array, and I just increment I. And inside the loop, I trade computation for data by means of, for example, I compute here I plus 3 times q, which would be, one third of the array away from here, right? So instead of having four variables going in lockstep like that, I'm going to have one and compute the rest every time in the loop. So it looks like a reasonable thing to do. It didn't improve any speed, right? So again, I'm showing you this to show you just how many ordeals I went through. This was an important topic, by the way, so I really had to do that fast. So let's take a look at the next attempt. Pass number 4, this is actually simple. Get rid of the multiplication by 3 because it's unnatural. I'll go back one slide. So here we have a multiplication by 3. And it turns out multiplying something by 3 is more expensive than multiplying by 2 or not multiplying at all, right? So let me eliminate that multiplication. So I pre-compute it here. Q2 is Q plus Q, and then I replace the multiplication by 3 with the addition Q2 plus Q. So that actually finally it moved the needle. So I got a 3% improvement, and that night I slept very happily. But yes? Would the compiler move the common sub-expression? Sometimes it does, sometimes it doesn't. So that's a problem, so the compiler has only this much resources to keep track on, try different things and stuff. So it doesn't really try everything. It should, I agree. But actually, the meat is 3% is nothing. I mean, for this algorithm, we've got to look like the fifth at least, right? So let's try something more radical. How about this? If only there were a way to optionally add a value. So here, let me define this function optional that takes a flag and the value. And here's how it works. If flag is 0, then optional returns 0. If flag is not 1, then it returns that value. So it's quite literally an optional value. C++ programmers, please replace mentally this convert to int 32. It's a cast. It's actually an implicit conversion to int. Just put int here. It's a minus int of flag and value. This function quite literally took me a lifetime to write, because it's it's an integral of a number of mini insights that I had over years, and it's like actually I could do this simple arithmetic that's going to work. And here's how it works: if flag is 0, minus 0 is 0, and 0 and anything is 0. So I'm done. I return 0. So far, so good. If flag is 1, then taking it to an int is the integer 1. But taking minus of that is what? Yes? Sorry? Right? It's a remarkable number. It's all ones in binary. And it's going to become a mass that when you AND that thing with anything, you're going to get that thing. Right? So I got a magic device. And I'm pretty confident I'm gonna give this talk until some compiler writer is gonna be in it. And at that point, that guy's gonna be like, oh, we gotta do this in the compiler. Right? Nobody does it right now. So I got this little function. Yes, please.
What about the cases when the flag is actually not 0 or 1? Because it
What if the flag is not zero, neither 0 nor 1? I don't handle that. Yeah, I didn't know it's not guaranteed in C. I knew C# has there's a discussion, but in C++, is there such a case?
Yeah, in C++, anything non-zero is considered a true.
Yeah, but actually, int of Boolean true is 1. When it again replace this with int of flag, and that's true. That's 1. That's the integer 1. So I'm fairly confident that this is correct. Even in the most obscene implementations of C++. Today's implementation really look at 1 bit. So, OK, great. So, yes? Sorry? I didn't work with the digital Mars C++ compiler. Oh yeah, the decompiler has like the GCC and the LDC backend, and they both work well with this. So yeah, so it doesn't matter which source language you use to some extent, but essentially as soon as it gets the logic down efficiently, it's just going to work. So now we have this mini function, which is kind of a static inline in C++ function, and you could make it work with unsigned and whatever. So the idea is the same. So then we have, how about this? So we're going to go, let's use it. We're going to go m0 equals I minus optional of this guy, right, depending on the condition. So this is not a branch any longer. And again, this is not a branch any longer. So I only have one branch left. So let's measure this guy. And here's where it gets really interesting. You get a 16% loss on organ pipe. You get an 18% loss on sorted. So friends, if that were the only data you tested on, you'd move on. Right? You see my point? You want to measure on different data shapes. However, it's 23% faster on random 0, 1. And by that one, I was like, there's something interesting here. And it's over 2 times faster on random and on real data, which is the most interesting stuff we want to work on. So this is a huge win. And my question to you is, why did I get a loss in performance on organ pipe? Why did I get a loss on sorted? Why did I get a huge win on random data and on real data? Yes, please. There's no difference in inlining. Optional gets inlined. Yeah. Yes. Huh? When it's sorted, the branch predictor is going to have a good day. And with organ pipe, it's going to have a good day except for one hiccup in the middle. It's going to have like one bad prediction at the beginning, one bad in the middle, one bad at the end. That's 3 for the huge array. So awesome. So for the cases where the branch predictor is having an easy, unsurprised job, it's just going to do faster than optional. Because optional is extra logic. It does extra logical operations and extra little things and masking and whatnot. However, whenever we move to surprising data, such as random 0, 1, random, and real data, then the branch predictor is going to be swamped. It's not going to be able to predict things correctly, and is going to lose to our approach. But wait, there's more. We could actually use optional again, so I added just a little more arithmetic here, nothing complicated. I don't expect you to like grok all the details of the code, but if you see down on it, you can eliminate the last branch too. So you use optional everywhere, and there's no more branching, 0 branch inside the loop. However, I noticed it's still good, but it's not as good as the previous version. And guess why? So at this point, when you have 2 pieces of code that are, stumping you, you're going to have to look at the generated code. You go to Godbolt, there's these assemblies for C#. You can, essentially go and look at the source look, right? And guess what I saw in the disassembly? I saw that the compiler was smart enough to eliminate this branch itself. So the compiler transformed this into a conditional move. So it was already doing the last step. He said, you know, Andrei, you've done all this work. I'll help you here. Right? So yes, that's what happened. So essentially, it's good to actually look at the end result of your compilation process to figure out exactly what happens. And what was happening was indeed the compiler was doing part of the work. It was lifting part of the way for me. Great. There is actually another thing I tried, which was not very successful, but I think it will be successful in other cases. You can write a little function that's also inlined, which is if-else. And you have a Boolean flag, and you have an integer which will be returned if the flag is true, and you have another integer v2 which you return if the flag is false. And let's see how it works. Look at the first line here. It's the same, right? Yes? Let's look at the second line. I'm converting the flag to an int, which is like really int of flag. And I'm taking int of flag minus 1 and v2. So let's see how this works. If flag is 0, the first line here is going to take 0 minus 0. This whole thing values to 0, right? But the second thing goes from int 0, 0 minus 1 is, right? Minus 1, that ended with v2 is going to give you v2, so you get the second value. If the flag is 1, the first line works just like before, and the second line is going to be 1 minus 1, 0, and you're done, right? And it didn't work well on this particular algorithm, but I'm pretty sure that if you paste this in your code, if-else, and you try it, you're going to find situations in which it does save the day. Awesome. So I've been trying this, and if-else didn't help here. And again, it's because the compiler was already at work replacing that test with a conditional move. Cool. Since we have just 2 minutes left, I'm going to stop here, and I'm going to. Wait, this was. I'm not sure why this. Okay. So we're going to stop here, and I'm going to take a few questions if you have. Yes, please.
Do you have any kind of framework just to capture the real data before you're calling the function to have like the real input data?
A framework that captures the real data. Yeah, but it's more like, opportunistically, you just, you have your files, you have your data, you have your inputs. So there's nothing formalized about the pre-processing part. Yes, questions? Yes, please.
To use profilers like video?
Oh, yeah. So profilers are a big part of optimization. So, as we discussed in the opening, you got to know what you're doing. You got to measure as the first step. And profilers are a huge tool, especially for subtle things such as cache spills and all of that. My data is too big or my code is too big. And these things are very easy to understand without a profiler. So definitely I would recommend. Actually, Intel was very nice. They called me and they gave me a free copy of VTune. So I should kind of pay them some lip service here. VTune is a great product. Right?
It is a great product.
Sorry?
It is a great product.
It is, yeah. So, I'm feeling good. I'm not really whoring myself here, Yes?
Have you considered making something like a cache simulation in order to see what's going on?
Cache simulation. That is very slow, actually. So what I've done way in the days of my grad school, it was you could do that kind of stuff on a much less powerful machine, right? So you can do I have a very, very weak machine, and I'm doing simulation on it to figure out cache effects and stuff. But profiles are going to show you these cache effects quite nicely. All right. Yes, please.
Could you say a few words on, is it still as relevant today, techniques like strength reduction for instructions?
Strength reduction, so let me kind of explain to everybody. Strength reduction is a compiler optimization. If you Google for it, you're going to find actually a few pages written by compiler writers. And strength reduction is you take an expression and you try to express the same expression with cheaper operators. Like you replace division with multiplication, and you replace multiplication with addition, and you replace with shifts, and you know. For example, there is a well-known paper that allows you to replace division by a constant with a multiplication by another constant and a shift. And everybody does that now. And that would be an example of strength reduction. But that said, there is strength reduction that, how should I put it, that you can use creatively in ways that compilers can't figure out to rewrite algorithms with less strong operations. And I have a talk about that. If you Google for my name in Fastware, you're going to find a talk of mine last year which discusses exactly strength reduction. All right, I'm here and the other people are done, so go get some food and coffee. Thank you very much for being here. You've been great. Awesome. Thank you.